Good afternoon, everybody. Welcome back. Hopefully, you had great knowledge by attending a practical session this afternoon. Are there any question about the what you saw this afternoon in the lab? Obviously, you guys monitor the texture measurement, compression test, puncture test, and then TPA. You saw TPA. We will be talking more about that tomorrow morning. And then you also looked at the viscosity measurements. On Friday, we will do more rheological measurement. With that, I like to continue our discussion about the rheology of food materials. Before we looked at classical example of viscoelastic properties, because yesterday we looked at the elastic properties and this morning we looked at the viscosity, viscous properties of food material, where we know Newtonian, non-Newtonian fluids, time independent behaviors, we looked at it. And then this afternoon we started looking at the viscoelastic properties, classic example of how to calculate the theoretical viscosity, because it is not possible to measure the viscosity of solid materials, and this is only way we can at least have some understanding of what would be the theoretical viscosity values and what would be the magnitude of those values would be. Now I like to direct our attention to the again viscoelastic properties, but in a different approach, not as a compression test, but more of a oscillatory shear measurement. So if you look at if you remove the stress, all energy required deformation is recovered if it is ideal solid, right? Because ideal solid is elastic one, and what it happens is primarily a spring model. So whatever you recover, it will come back to the original position. All the energy is recovered. But in the viscous model, ideal fluid, all the energy is dissipated. Nothing is coming back, all dissipated. But the real bodies neither ideal solids nor ideal fluids. They are combination of viscous nature and elastic nature. One of the prime example is cheese. Just give an example as a cheese, but apple, orange, potato, things like that are mostly is viscoelastic. So we are going to continue our discussion in terms of how to characterize the food material, viscoelastic nature of the food material, and then determine the rheological properties of viscoelastic material. In this method, you perform by imposing a sinusoidal stress and measuring strain, or vice versa. So you can impose stress, oscillating stress, sinusoidal stress, and you can measure the strain, or impose strain and measure the stress. There are equipments which are stress equipment, you can apply stress to get the strain. There are equipments you apply strain and then measure the stress. The main point here is whatever we talked so far, because those are all macroscopic evaluation, this is more of a microscopic measurement. When I say microscopic measurement, I don't mean to say go deeper, but it's surface measurement. You are just applying the sinusoidal stress or strain on the surface of the material. So it's basically a surface property, not as an internal property. So the reason for doing this is if you measure these properties, you will be able to correlate with the structure function properties. That's the idea behind it. So that way you will have better understanding of what is inside the material microstructurally, structure wise and function wise. Then you can try to correlate that with the dynamic properties, dynamic rheology property, what you can measure in this test. So how do you do the dynamic testing? Basically either oscillating strain or oscillating stress input. What you see here is a sinusoidal wave going from negative to the positive and then negative and then positive. One way to look at this is the current we get from the outlet, those are all alternating current. In the similar way this can be viewed, this is oscillating. On the other hand, when you look at the surface of the material here and then you have on top of that you apply the oscillating stress or strain, and that's what it is. So when you do oscillatory stress or strain, you apply the sinusoidal wave, sinusoidal stress or sinusoidal strain, and once you apply stress you get the strain. If you apply strain you get the stress output. Are there any questions on this one? This is different than what we have been talking so far. We have been talking about compression testing, but this is totally different than the compression testing. So here the sample is not mechanically damaged, nor its internal structure is disturbed. So we are not damaging the sample, we are not disturbing the internal structure also. In previous cases, we are really compressing sample, so damaging the sample, and structure also get disturbed, because after the test the sample is no more use, you throw them out. But here it's not the case. You can still use the sample for other microstructure evaluation, functionality evaluations. So this way you can do everything, you can do the dynamic testing of the sample first and then do this for the same sample, you can do the microstructure and functional properties, because our samples they are not homogeneous, they are heterogeneous. So if you take different samples for different testing, then there is not much correlation you can do. This way you can do correlation. For example, if you take the case of cheese, you can cut the sample of cheese small disc, like okay, I will go back. You can cut a sample of cheese for doing the compression testing. So once you do the compression testing, that sample is disturbed, damaged. You cannot use the same sample for doing structure and functional properties. You have to go back to your batch of cheese sample, get a new sample for structure and functional properties. Because it's not homogeneous sample, your microstructure you are going to evaluate in the new sample will be totally different, and you cannot use the microstructure images of that new sample for correlating with the compression test you are trying to do. So that cannot be correlated. But in this method you can definitely correlate, because sample is not damaged and you can use the same sample. That's the idea behind this test. So that you will really get a good lot of new information and more additional information which will help you with the product development. Again, this test takes a lot of time, a lot of patience. We will talk more on that down the road. So thus it measures the surface phenomena to study the microstructure of a sample. So it is much more useful in that way. Okay, it's a viscoelastic property, oscillating shear stress. You are going to apply stress, get the strain, or vice versa. So here there are spring model and the dashpot model also. spring model is for elastic response and dash part is for the viscous response. So, it is shear stress is a function of shear rate. So, what you get is the modulus which is G. So, while oscillating test strain is a function of time. So, because of that you get the initial strain is sine of Wt, W is angular velocity. What it is when you rotate your sample with a probe, then you are basically doing angular velocity. You are applying the angular velocity, and R0 is the maximum strain exert to the spring. So, basically what you get is shear stress is equal to constant G maximum strain times the sine of omega t. So, this is the output from the elastic response, the spring model we assume in the sample itself. So, in this here what you see is a spring model. You have a spring and the spring is getting rotated, or you are just doing the angular velocity, you are applying the oscillating shear and you are measuring the strain. Okay. In this case you are doing the strain input and you are measuring the stress output. So, strain input is open circle. So, this is -1 and you are going it to the +1 and coming to the -1 and then going to the 0, and that is the strain input. So, as you input the strain you are measuring stress. The stress is basically is the solid circle. So, stress response is on solid circle, that is what you see here. So, this is for the dynamic test spring model. So, strain input and the stress response for a spring type solid. Okay. So, this is for the spring type solid for the spring model.
Sir, in reality, how this kind of strain is input? I mean to say this strain input is given in which form, like how it is done?
Okay. How it is done? Basically, I think you saw the rheometer this afternoon. So, there was a sample placed on the disc in the platform, and then there is a probe was rotated, right. When it rotated, what it does is basically when you are rotating it, the starting point is -1 or 0, and then when you are shearing it, what you do is basically you are applying the strain. Okay, starting here, and then when you are rotating it, that is basically the strain applied. So, once you apply the strain, the corresponding stress is experienced by the load cell in the system and it gets you the stress value. That is what is happening in this test. Good question, thank you. The question was how do you apply the strain, how do you get the stress? Basically what you are doing is applying the strain like this, and then corresponding stress is experienced by the load cell in the rheometer, and that output is coming to you as a data, and that is what it is. The other one is dashpot model. It is a Newtonian behavior. So, Newtonian behavior only we can assume here, and again stress is a function of strain, and because of the dashpot model, the constant here is the viscosity. Similar action to the piston. So, when you have the shear rate is a function of time. So, you get angular velocity times the maximum strain, function of cos omega t. Previously for the spring model it is sin omega t, but for the for this dashpot model, it is a cosine of omega t. So when you substitute the strain with the viscosity uh, and the maximum strain, what you get is, instead of the shear rate, you get shear stress and the viscosity, because shear viscosity is nothing but the shear stress over shear rate in classical sense. That's what we did in the viscosity model. Uh, in the elastic model, we get modulus of elasticity as a function of stress over strain. Um, the spring model is stress over strain, and here it is shear stress over the shear rate, and you get the viscosity. So you substitute the for the shear rate, you substitute stress and then viscosity. So that's what you get here, because this is for dashpot model, and for spring model, this is shear stress is a function of G, which is the elastic modulus. This is elastic modulus, and then maximum strain and sinusoidal sine of Wt. Here in the dashpot model, you have strain input again, and the strain input is the open circle, and the stress output is a solid square. And dashpot model it's a dashpot. So when you are rotating it, it's going to push, or it's going to flow, and then it's going to keep flowing, and that's what you get. So if you compare this strain input and stress output, strain input is same for both the elastic and viscous model, right? This is viscous model, strain input is like that. When you go back and check the spring model, again same strain input, but the stress output is different. For pure elastic model, the stress and strain are in phase. They just follow the same sinusoidal form, both the strain input and stress output for pure elastic model. But that's not the case with the viscous model, where strain and stress are 90-degree apart. So that's what I am talking about, 90-degree apart. So the maximum is here, for the strain maximum is here, for stress maximum is here. That is 90-degree apart. That is for the dashpot model, viscous model. So spring model, they are in phase. For dashpot model, they are out of phase by 90-degree. So what it means is, if your sample is more viscous in nature, your phase angle, the phase angle number you get from the system should be closer to 90 if it is more viscous. If it is more elastic, it will be closer to 0. So if it is purely elastic material, phase angle will be 0. If it is purely viscous material, then phase angle will be 90. Follow me? Does it make sense? So phase angle will be between 0 and 90 for any of the sample you may test or you may characterize. So in terms of theoretical aspect, that's what I said here. The strain and stress are in phase with each other. For viscous liquid, the response of stress is 90-degree out of phase to the strain. And it will be similar if you have a stress input and strain output. The example I showed you here is a strain input and stress output. So the strain is 90-degree ahead with respect to measured stress. So if you substitute that information here, the shear stress is equal to viscosity times angular velocity times the maximum strain cosine of Wt plus phase angle. So when you are, if you are measuring viscoelastic material, the phase shift angle is between 0 and 90. What it means is it's a combination of spring and dash part, combination of elastic nature and viscous nature. Similar to what we discussed before, here also same analogy for viscous model, not viscous model, for the Kevin-Wagin model, which is creep, right? Kevin-Wagin model is a creep where dashpot and spring are parallel, and in that case you apply the constant stress and then monitor the strain output. Strain output, so that strain output is the output you get, and you can use the modeling for the dynamic test. So here total stress is stress of spring and stress of dashpot. Because we input strain, we measure the stress, right? Previously we talked about inputting deformation, inputting strain and measuring the previously we talked about deformation and stress. Same thing here. So total stress is stress of spring plus stress of dashpot. Strain is equal in both. That's what we talked about before also. It's the same concept but different types of loading here. This morning when we talked about things, what we talked about is basically applying in compression, here sinusoidal wave. So that is the only difference. So here the Kevin-Wagin model, this is strain input similar to what you saw in the other screen. So with the strain input of this much, they are parallel to each other. You are connecting spring and dashpot connected parallelly. So when you have a strain input like this, the output is basically viscoelastic fluid, a Newtonian liquid and ideal solid. And then so what you see here is there are three different graphs. One is ideal solid and Newtonian liquid and viscoelastic fluid. So the ideal solid is this one, the open triangle, that is ideal solid, which is in phase with the viscoelastic fluid. They are in phase with each other, and then Newtonian liquid is which is 90-degree apart, and that's what you get when you consider the spring and dashpot parallelly. So they are 90-degree apart, and that shows the dashpot, how the viscous model works. So the viscous model, Newtonian liquid is this one, and then viscoelastic fluid is this one. So they are 90-degree apart. So when you consider this one as a Kevin-Wagin model, they are in parallel, that will be your output. The Maxwell model, dashpot and spring are in series. The total strain is strain in dashpot plus strain in spring, but the stress is equal in both. Similar to what we saw in previous cases. In compression testing, stress is equal in both, but total strain is in dashpot plus strain in spring. Here we are looking at the strain input and stress output. So for dynamic test, viscoelastic fluid, same thing here, viscoelastic fluid, and then ideal solid is here, they are in phase, and then viscoelastic fluid is 90-degree apart. So similar characteristics you also get here when you consider both spring and dashpot in series. So when you combine this elastic Maxwell model and the Kevin-Wagen model, so that's why these materials are more complex than the individually. So we are combining those two, and then you get the complex modulus. When you combine the Maxwell liquid and Kevin-Wagen solid model, so you get the, which is the total resistance of a substance applied against applied strain. So what you get is maximum stress over maximum strain, and that gives you the complex model. And the complex modulus has both the Kevin-Wagen solid and Maxwell liquid, and one is real part, the other one is imaginary part, and from there you can split them out. So the complex modulus has a G star, which is elastic modulus plus the imaginary part of complex imaginary part of viscous modulus. So sometimes what they do is they measure, they also call as a storage modulus for elastic nature, and the viscous is also loss modulus, because if it is purely elastic material, you can store all the material, all the energy, nothing is lost. That's why it's called storage modulus. Elastic modulus or storage modulus. For viscous, it is viscous modulus or loss modulus. Real part is recoverable, imaginary part is lost. That's why it is loss modulus, and G prime is the storage modulus. As I said before, storage modulus is G prime. Stress energy is stored during the test, which is real part. So if substance is purely elastic, then shift angle is 0. So you get the only G prime, which is the G star. Complex modulus is same as the storage modulus, because when the shift angle is 0, there is no imaginary part. G double prime being 0, so we get the complex modulus only in real part. On the other hand, the viscous modulus or loss modulus, whatever energy used to initiate the flow, it's lost, so transformed into shear heat, so you get the imaginary part. So if the substance is purely viscous, then shift angle is 90 degrees, and then G prime is 0, so you get only G double prime, which is viscous modulus. But our materials are viscoelastic, so any test you do, dynamic test you do for your sample, you get both the G prime and G double prime, storage modulus and viscous modulus, storage modulus, viscous modulus, or elastic modulus, elastic modulus and viscous modulus, or storage modulus and loss modulus. So that is how you interpret it. Elastic, viscous, storage and loss. So in terms of measurement, this is a typical instrument you use. This one is in our lab. It's called viscoanalyzer, which can be used for both the viscosity measurement and also for the dynamic rheology measurement. You can do the oscillatory shear test here. This instrument is a constant strain equipment, so you apply strain, get the stress output, similar to what Sushil has in his lab. strain input, stress output. Correct? Yep. So this is what you see here is you have system here which controls your instrument, and then you can have all the variables input in the system pre-measurement, and this also has the heating system, external heating. So this has the heating element here, and this is the temperature controller where you can control the temperature. You can also do heating experiments and also cooling experiment. So you can follow the profile of the sample in terms of what happens during heating and cooling. You can really mimic the actual processing happening. What happened, like for example, if you take example of cheese, cheese is used in a lot of applications. Can somebody tell me one application where you use cheese? Pizza, exactly, yeah. No brainer, right? You don't have to think too much because we eat a lot of pizza these days. So we apply it very well. So if you want to know how your cheese is going to behave at higher temperatures, so you can do this kind of test and find out whether it's going to be elastic material or more viscous material during heating. And that will give you more information during product development. So you can modify your composition of the cheese based upon what you are looking for. If you want more viscous cheese, then you have to modify the way you make the cheese. By doing a lot of modifications, you can do that. Or if you want more elastic cheese, which we don't want, typically we want to have more moist cheese, more viscous cheese, more stretchy cheese, and that will have a better consumer acceptance, right? If cheese is not stretching, it's not called cheese, right? Well, not really, depending upon the application, right? If you are going to eat pizza, then you want more stretching cheese. If you are going to eat cheese in burger, then you don't want more stretchy cheese. More you want to have some softened cheese so that it doesn't flow out of the burger. You don't want to get messy, right? So that is idea behind that's how they use the information to produce different type of cheeses. This is a close-up view of the what you apply, what kind of test you do. So in the measurement, you have the bottom plate, and that can be heated and cooled, and then the sample is placed in between the disc and the bottom plate, and the disc is where you apply the sinusoidal wave. There are a lot of issues with this test. Main issue could be, depending upon what type of sample you put in, there could be some slippage. If there are more slippages happening, your results won't be accurate. So one way to reduce the slippage is you can have a sandpaper attached to the disc so that it doesn't have any slippage. So if you have something sandpaper attached to the disc on the top, and that can, when you rotate it, when you oscillate it, there is no slippage. You want to make sure that there is no slippage while you are doing the test. If you have a slippage in your test, then your results you get won't be accurate. You won't be able to reproduce those results. So that's one of the drawbacks you get in the dynamic test. A lot of times slippage is a main problem in the dynamic test. So basically you have a rotor which deflects with a sinusoidal time function alternately for a small angle, and the sample is forced to strain, resisting the stress. So amplitude of stress is related to the nature of the sample. So whatever stress you are collecting, it's related to the nature of the sample itself. So when you have the complex modulus and phase angle, those are the numbers you get from the measurement that can be easily converted to the corresponding G prime and G double prime using the equation I showed you here. So when you get the complex modulus and the phase angle, so using these equations, complex modulus as a function of phase angle, you can get G prime and G double prime. which is storage modulus or elastic modulus, and this is the viscous modulus and the loss modulus. So in essence, what you get is in the test, from the instrument, you get the complex modulus and the angle, phase angle. And then computer uses this relationship to give you the storage modulus values and loss modulus values. Because you know the relationship and the software is taking into account of that, you get the storage and loss modulus. So in essence, what you are measuring is the complex modulus and the phase angle. From there, you are calculating our system is calculating storage modulus and loss modulus for you. So with the sinusoidal wave, you can plot a curve of moduli as a function of frequency, and that's what you probably saw at today's lab, where you have the frequency sweep experiment they did. Amplitude. Okay. Amplitude. Oh, okay. So in this test, what happens is, if you want to really have a quality data output you need to get, first thing you do is find out the linear region, linear viscoelastic region of your sample. What does it mean is, you have strain input, stress output, right? When I say strain input, stress output, basically you get the modulus value out. So strain input and stress output. So you basically vary the frequency and try to get the stress output, right? So your stress output should be, so if you have frequency as a function of stress, so your stress will be like that. So when you have the stress like this is where you are trying to find out the linear viscoelastic region. When you have a constant stress coming out, that shows the linear viscoelastic region. When stress is declining, then you are going in the non-linear viscoelastic region. You want to do all your tests within this linear viscoelastic region. So this would be the maximum stress you can employ for further amplitude stress or amplitude frequency test and so forth, so that you can see the storage and viscous storage and loss modulus values or elastic and viscous modulus value. So this is the one we have to do in the beginning before you even try to do other tests, amplitude frequency test or frequency sweep or temperature sweep, whatever you want to do. So this needs to be done for your sample, absolutely needs to be done, so that you can fix the stress value in the linear viscoelastic region. So what is linear viscoelastic region here? Meaning that linear viscoelastic region is where whatever strain you are applying and then output stress you are getting, whether during the sinusoidal wave loading or unloading, it will be the same thing. If you go to non-linear region, then you are not going to get, you are going to damage the sample, or it is out of, when I say damage the sample, I don't mean actually damaging sample, but you are going to really compress the sample, and that's not going to give you the correct results. So important point is, you need to identify the linear viscoelastic region. You can work on this stress. Once you identify this stress, use this stress in your future test. That way you get the accurate result. If you don't do the test and then you randomly select your stress, that will not be right way to do that. So this is the bottom line. If you don't do the test and then just like that go and do other test, other parameter input, output, you are going to get output, whatever results you are getting, that won't be right one, and that won't be reproducible if you are not working in the linear viscoelastic region. Some of the commercial applications, different polymers you can employ, different food and biological materials, gels, plastic materials. Again, as I said before, this rheological application of food material happened only the last 50 years. Before, they use it for polymers and plastic materials. And these technologies are borrowed technology for the food materials, right? Because previously, olden days, there is no product development. Whatever is available, they got it, and then life is good, right? I mean, there is no newer product development. Whatever naturally available, they were able to cook it in different forms and eat it. And then slowly, people started thinking in the sense, no, this is getting old. How many days I can eat the same potatoes, carrots, beans, and things like that? There should be other ways to modify, add value to this product, get a newer product, right? When did the cereals came? When did these chips came? When did we cut the chips?
Consumer preference change.
No, but I'm talking in real term, real time. What is that? Yeah. So then only after that only. So in 1935 is long time ago. But personally speaking, I came to know about chips and all when I went to US, which is 33 years ago. You know, so it all depends upon what the consumer preference is, right? It could be available, but I don't think in India and all there was a chips available 1940 and all. I don't think so. Anybody, I mean, we are talking about your previous generation, but I think when the lifestyle changes, people tend to look for newer food styles, newer things. So these are all borrowed technology, and only even dynamic rheology test and all, those are all started doing only recent years, right? 40, 50 years ago only. Before that, there was no studies at all, right? Even if you look at the literature, I don't think anybody did anything about the dynamic rheology of cheese or dynamic rheology of this and that like that before 1970 and all, or 1950. What is Google is saying?
It says Uncle Chips was the first chips that was introduced in India. 1992.
Okay, so that should be correct, right? I mean, I don't, yeah.
Before that, never saw it.
So it's a recent development. So a lot of challenges also there, and that needs to be also looked into it also. So when you look at this test, advantage is you can predict the behavior and characteristics. You can do process modification in your product. You can also do the structural evaluation. So that way it has a lot of benefit, and that's one of the reasons people do this kind of test in their labs and all. Main disadvantage limitation is it is tedious process. You have to really, for your solid sample, you have to really make the uniform sample. Thin sample, 2 millimeter, 3 millimeter thickness sample. Sometimes it is very, very difficult to get uniform size sample, right? I don't know any of you cut the samples today for the test. No? Okay. Okay. And then it's a complicated mechanism also, because we have to do a lot of input and output. You have to look at the linear viscoelastic region and take the sample out, and then do the other test for your sample. More importantly, this instrument is costly equipment. Typically, it runs for anywhere between 60,000 to $100,000, 60K to 100K. Compared to Brookfield viscometer, probably I can get it in 5K instead of 60K or 100K. But issue here is when you are measuring viscosity of your sample, you definitely need to characterize them, whether you want to find out whether your fluid is Newtonian or non-Newtonian. This $5,000 equipment cannot give you that information. All it can give you is the only one viscosity number. This cannot characterize your fluid. This one can characterize. So if you are in the product development area, if you have a bigger industry, all the industry in bigger industries will have in their R&D lab, they will have this rheometer, because it's worth having it in their place when they do product development work, if they are interested in characterizing their fluid. But if they just need only one viscosity number, Brookfield viscometer will give you that information. The numbers you see is from US model numbers, okay? But here everything is improved. Even in India, you can get it much cheaper than this value here. Or if you get it from China, you will be much cheaper also. you don't do the work. But I don't know how long that instrument will work, but that's what it is. Because the instrument that we have in our lab, when I joined the lab 25 years ago, I got this instrument, rheometer, viscoanalyzer. Still it's working. But I don't know, that could be the case when you get the instrument from China. So, and the same thing true with the extruder also. Extruders are very expensive from US market, but it's very inexpensive from China market, because I think their labor is cheaper, and then the equipment, the monitoring systems and control systems they have, those are all less expensive in terms of material itself. So it's all about the lifetime depreciation of your product is very important. In fact, I have a small lab scale extruder in my lab that came to my lab 10 years before I joined. So it is 35 years old. It is still working, and we still do things with that instrument. The bottom line is, any instrument you get, you have to keep working at it. If you just let it rest for some time, it dies. You cannot do anything with that. So you have to keep running it as much as possible. Here also, the correlation is difficult in case of food materials. Typical characteristics are different. So you will get a lot of variations in your results. What is the concept? Dynamic viscosity. Okay, there are 3 different viscosities values out there in the literature. One thing is apparent viscosity, and that's the thing we are going to measuring when you characterize these samples. That is called apparent viscosity. Dynamic viscosity is the one when you have the medium is some type of liquid. That's what you are measuring, viscosity of that liquid. And then when you use some type of flow models, like for example, this is your liquid, you want to test the viscosity, and then you drop a ball. When your ball get dropped, you measure the time it takes to travel from the top to bottom, and then measure the time. So from that value, density of the ball and density of the liquid, and do all the calculations, the viscosity value you get, it's called dynamic viscosity. that dynamic viscosity is different than the apparent viscosity you characterize, you measure. The reason it's called dynamic viscosity is it is in relations to the density of the material you are measuring. That's why it's called dynamic viscosity. And that's not the actual viscosity. Well, it's a viscosity of liquid you are measuring, but because of the systems you employ, it's called dynamic viscosity. What about kinematic viscosity? It's the viscosity of liquid divided by its density. So meaning that kinematic viscosity will have a different unit. It's viscosity over density, so you will have a different unit for the kinematic viscosity. So it is viscosity over the density of the material. So in the last 2 days, we discussed about a lot of things. We started with the definition of how we define the texture, because texture is everything, right? It involves mechanical properties, involve the rheological properties, structure, you name it, everything goes into that. So we are trying to study the individual things. So then we went to the mechanical properties, where we looked at the stress-strain relationship, force deformation, stress-strain relationship. We looked at the different point of interest in terms of stress-strain curve, and then we looked at the Poisson ratio, and then we looked at the degree of elasticity and plasticity, and then we also did the both the compression test and the tensile test, and then we went on to look at the viscosity of different fluids, Newtonian and non-Newtonian fluids, and from that we went into the viscoelastic properties of the material. We looked at two different ways of looking at the viscoelastic properties. Classical example is doing the compression test, viscoelastic properties of the material, and then because the elastic properties we can measure, we can only theoretically compute the viscosity properties of the material, of the solid materials. Then we looked at the dynamic test, where we looked at the complex modulus, elastic and viscous modulus, and then importance of those measurements in the product development area. So any questions? So from tomorrow we are going to look at the texture profile analysis, and then looking at the some of the functional properties of dairy products, and what other measurement we are going to have, and then we are going to shift our gear to the sensory analysis. It's very important that when we talk about instrument systems, instrument way of measuring things, we also need to make sure that we discuss about some sensory analysis, because at the end of the day, whatever product we are trying to develop, consumers should accept that one, right? So no matter how much instrumentation we use, that may not be all we should do. We have to include sensory analysis also. So we will be looking at that. And then moving on, then on Thursday we will be looking at the topology of the food material, which is a newer concept. It's evolving and it's much more cumbersome to do. There are instruments available, new instruments are coming up, so we will be doing some discussion on that also. And then Friday we go to lab and do more practical activities.
So actually, as you were just concluding the whole part. So in the itself, it's written that tribology characteristics of food reptiles. So what is this tribology thing?
That's what we are going. I said we are going to discuss on Thursday. Tribology is all about surface characteristics. When you, I mean, this is sinusoidal wave. There in typology, you basically move your thing in a very gentle, well, in a regular fashion, so that you can look at the shear properties and things like that. That's what the typology is all about. So sit tight, we will cover the material. So I was special. I don't work on that field, but it's a very interesting field. So we will have some information to share, and we will discuss more on that. So tomorrow when we come back, we talk about texture profile analysis. We will do some activities in our discussion. We will do some calculations. We will try to compare some numbers and see how best we can describe, because that is one of the classical tests everybody does these days, right? Texture profile analysis, because that's a test we all think that mimics the how we consume the material.